Howdy, howdy, this is Mr. Potter. In our previous two lessons, we've been talking about how to find volumes. In our first lesson, we talked about volumes using cross-sections. And in the second day of section 7.3, we talked about rotating a given curve about the x-axis. So what I want to talk about today is how do we deal with situations when we're taking a rotation around a line that's different from the x-axis. So I want to go through a few examples here. So for my first example, I'm going to be dealing with a simple parabola, y equals x squared, and I'm going to be dealing with it on the domain from 0 to 2. But instead of rotating about the x-axis, I actually want to rotate about the line y equals 4. So I'm going to graph my parabola just to kind of get a picture of what's going on here. And of course my parabola has the traditional parabolic shape. And if I'm going out to 2, my line y equals 4, this is the line that I'm rotating about. And of course it happens to just meet at this point. So from 0 to 2, I'm actually rotating about this line here. So again, my thickness has to be parallel to my axis of symmetry. So my thickness is going to be dx for this situation. But when I'm looking at my radius, just like we were talking about the area between curves, because I'm no longer talking about just dealing with the x-axis, my radius is really top minus bottom. So for this, my top is going to be the curve y equals 4. My bottom is the graph. So this is really 4 minus y, or 4 minus x squared. This is the radius that I'm going to be dealing with. So I need to come up with an area function. And I remember, ideally, I want to come up with an area function in terms of x. But my cross sections are circles. So when I look at a circle, my radius, which is going to go from the center to here, this is actually going from my axis of rotation to a point on the graph. I can draw it here or here. But my radius ends up being 4 minus x squared. So my area, which normally is pi r squared, is going to be pi times 4 minus x squared squared. And of course, this is something I'm going to have to integrate. To determine my volume, I have to take the definite integral of my area function of x, in this case dx. dx because my thickness, the thickness of this circle, the thickness of this disk, is my delta x, or dx. So I'm going to be integrating from x equals 0 to x equals 2, my area function, which is pi times 4 minus x squared squared dx. And that's an ugly integral. I'm going to expand that binomial. So I'm going to make it the integral from 0 to 2 of pi times 16 minus 8x squared plus x to the 4th dx. And this makes it a little bit easier to integrate using the power rule. So I'm going to end up with pi times 16x minus 8x cubed over 3 plus x to the 5th over 5, which I'm evaluating from x equals 0 to x equals 2. And so when I substitute, I get a volume that's equal to pi times 16 times 2 is 32. 2 cubed is 8 times 8 is going to give me 64 thirds. And 2 to the 5th is 32, so that gives me 32 fifths. Minus, now I'm going to do that exact same substitution, but all in terms of 0. Since every one of these terms includes an x, I get 0. And so this is my volume for this figure. Now notice that this figure looks different from what we were dealing with before. We're dealing with a function that's rotated about a different axis, and so I'm not going to get the same areas that I was before. So I want to do the same function, but now I want to take a look at this function rotated about a different line. So I've got the line y equals x squared, that's my curve, the same domain 0 to 2, but now I'm looking at it rotating about the line y equals negative 2. So what I'm going to do is I'm going to draw my graph y equals x squared, this parabola, but I'm going to be rotating around this line y equals negative 2. And in doing so, I'm going to get a circle that's going to go around. My center of that circle will be passing through this line, y equals 2. And the radius of this circle, as before, is going to be top minus bottom. So for me, this is going to be x squared minus a negative 2, or x squared plus 2. And so my area function, which is normally pi times r squared, would be pi times x squared plus 2 squared, or pi times x to the 4th plus 4x squared plus 4, because I know I'm going to need to expand this binomial to make integration a little bit easier. So I'm going to be integrating from 0 to 2 my function pi times x to the 4th plus 4x squared plus 4 dx. And so this is going to give me pi times x to the 5th over 5 plus 4x cubed over 3 plus 4x, which I'm going to be evaluating from x equals 0 to x equals 2. And so this is going to give me pi times 32 fifths plus 8 times 4 is 32 thirds plus 4 times 2 is 8. It's very important to think about this if I'm rotating about a line that's not the x-axis. I really want to think of it, if I'm rotating around a horizontal line, as finding my radius as top minus bottom. But if I'm rotating around a vertical line, then a couple of things change. So let's take a look at this function. I'm dealing with the same function, y equals x squared, on the same domain from 0 to 2, but I want to rotate about the y-axis. So this is going to be a little bit different. So I'm going to take this graph, and I'm going to take this curve, but I want to rotate about the y-axis. So as I did in my last lesson, I'm going to draw the graph's symmetry reflected across that line. And my thickness, the thickness of this disk, is actually delta y. So the thing is, when I'm rotating about a horizontal line, my thickness is delta x. But if I'm rotating around a vertical line, my thickness is delta y. And because of that, I need the area to be a function of y, not x. So looking at this circle, my radius is going from my axis of rotation to the point on the graph, which normally would be called x. And so I would have my area being pi x squared, but I need my area function to be a function of y. So I need to find a way to change x squared into y. Well, I've got a really nice way to do that, because y equals x squared. So my area function here equals pi times y. And so when I'm calculating my volume is going to be a definite integral of my area function in terms of y, because I'm rotating around a vertical line, dy, not dx, like I've been doing in all of my previous examples. In all of my previous examples, I've been rotating around a horizontal line, and so my integral has been with respect to x. Here, because I'm rotating around a vertical line, my integral is going to be with respect to dy. So I'm going to be integrating this function. This function in this case is pi times y dy, but my integral limits have to be in terms of y as well. So what I've really got is I'm going from a y value of 0 to a y value at x equals 2 when y is 4. So I'm going to be integrating from 0 to 4 this pi y dy. So the antiderivative of y is y squared. I get pi y squared over 2, which I'm evaluating from y equals 0 to y equals 4. And this gives me 16 pi over 2, or 8 pi. Now, if this looks familiar, this bullet shape that I'm getting by rotating around the y-axis is very similar to the bullet shape that I was getting by rotating around the x-axis in our day 1 lesson. And of course, that's because the inverse function of x squared is radical x. So that's why I see this y squared over 2, which we saw quite predominant in our day 1 lessons for section 7.3. So I want to do one more example of rotating around a vertical line, but I want to do it rotating around a non-traditional vertical line. So let's say I'm dealing with the same graph, y equals x squared, on the same domain from x equals 0 to x equals 2, but I want to rotate about the line x equals 3. So I've got my parabola, and my parabola is going to go up to 2, but my axis of rotation is actually going to be here at x equals 3. And so my disk is going to look like this. And just like when we were doing integrals with respect to x, we were looking at top minus bottom. When we're doing our integrals with respect to y, I want to think of this as my radius being right minus left. Just like when I wanted to find the area between two curves, if these were integration with respect to y, I would look at my rightmost function minus my leftmost function instead of top minus bottom. So in this case, my right function is this graph x equals 3 minus whatever my x coordinate is, like this. So if this is my radius, keep in mind that I really want this to be in terms of y. My area is the function pi times my radius squared, but I want an area function in terms of y. So if y equals x squared, then x must be the principal square root of y. And so this becomes pi times 3 minus root y squared. And if I expand this binomial, I end up with pi times 9 minus 6 radical y plus radical y squared is just y. So this is my area function in terms of y. And the thickness of this disk, because I'm rotating about a because I'm rotating about a vertical line, the thickness of this disk is dy. So my volume is going to be the integral from y equals 0 to y equals 4 of my area function in terms of y. So it's going to be pi times 9 minus 6 root y plus root y squared is y dy. So this is what I'm going to be integrating. So the antiderivative of 9 is 9y. The antiderivative of this, because this is really y to the 1/2 power, is going to be 6y to the 3/2 power divided by 3/2. And this is going to be y squared over 2. All of this is being multiplied by pi, and all of this is being evaluated from y equals 0 to y equals 4. So I'm going to have pi times 9 times 4 is 36. 4 to the 3/2 power is 8. 8 times 6 is 48. And 2/3 of 48 is 32. And 4 squared is 16. Half of that is 8. And so I end up with that for my volume. 36 minus 32 plus 8, or 12 pi. Now again, I'm dealing with rotations. So because I know the area of a circle involves pi, a lot of these rotations, whether it's about the x-axis or y-axis, involve pi as well. And if you notice, all of my examples have been dealing with some constant times pi. The trick is, if I'm rotating about any vertical line, because I'm rotating about a vertical line, the thickness of this cylinder is going to be in terms of dy. And so I need to find an area function in terms of y and integrate it with respect to dy. But if I'm rotating about any horizontal line, because a horizontal line is going to have that thickness dx, I'm going to be needing to integrate my area function dx. So that's what's really the key here. And of course, just like when we were talking about the area between two curves, if I'm looking at it from a dx perspective, I'm looking at it from top minus bottom. But if I'm looking at it from a dy perspective, I'm looking at it as right minus left to calculate these radii. It's very important to remember that, but it's fairly easy to do as long as you draw that cross section, draw that circle, and physically draw the radius to understand what's going on. So once again, this is Mr. Potter. Thank you for watching. Have a great day.